Now I can also use Punnett squares with dihybrid crosses. Di means 2, so now I'm looking at 2 traits at a time. Alright, and traditional Mendelian genetics, if they're all heterozygous individuals for both traits, I end up with 9 to 3 to 3 to 1. 9 individuals showing both dominant traits, 3 individuals showing the first dominant, the second recessive, another 3 showing recessive for the first, dominant for the second, and 1 individual who is recessive for both. So if we were to look at this, here I've got a parental generation that was purebred to be dominant for both round and yellow. These guys are recessive for wrinkled and green. My first filial generation is going to be 100% round and yellow, but they're carriers for both traits. So when I go to do a dihybrid cross from that first generation to create the second one, that's where I end up with that 9 to 3 to 3 to 1. Okay, 9 individuals who are dominant for both, 3 that are dominant for the yellow but recessive for the wrinkled, another 3 that are dominant for the round but recessive for the green, and then 1 individual who's recessive for both. So constructing dihybrid crosses, alright, we got to remember how to do all of this. So you are going to have a 4x4 square this time. Okay, so 16 total boxes. The hardest part for most students is to figure out the gametes from each parent to put on the top and sides of the Punnett square. You've got to use FOIL like you do in math class, first, outer, inner, last. Okay, and so if I take a parent generation who looks like this, okay, so let's say we're big A, little a for trait 1, and big B, little b for trait 2. Okay, treat this like math class. So put them in parentheses just like you would having an algebraic problem, and use the FOIL. So first is going to get me big A, big B, right? That's going to go above one set of boxes. Outer is going to get me this, big A, but little b. Inner gets me the little a with the big B, alright, and then last gets me the little a with the little b. Alright, and that's going to go across the top of your Punnett square. So you're going to have 4 rows and 4 columns that you have to deal with. You would do the same thing for the other parents, and then they would go down the side. Okay. So here's an example. Alright, each row and column has to have 2 letters associated. And then from there, you're just matching them up. Alright, and then you can count the number of round versus wrinkled, yellow versus wrinkled, so on and so forth, to get your 9 to 3 to 3 to 1 ratio. Now, we can do Punnett squares for monohybrid crosses, dihybrid crosses. Once we start needing to deal with more than 2 crosses, 2 alleles, it really starts to get complex to try and make a traditional Punnett square out of that. And so there are mathematical ways that I can do this without having to draw those boxes all the time. When we look at genetics, we're looking at the probability of producing the outcome of an offspring based on what we have as parents. Okay? So I'm looking for the likelihood that a particular event's going to occur based on the conditions I have. And so probability, I can use 2 different laws and simplistic mathematical laws to help me figure out the offspring. So I can use the multiplication rule. Probability that 2 or more independent events occurs as the product of individual probabilities. Can also use the law of addition. Probability that any one of 2 or more exclusive events happens together. Okay, so these are sort of independent events. This I'm looking for the combination of multiple things. All right, and so sort of think of it like flipping heads. If I know that my one parent is a head and a tail, so is my other. Okay, so 50% or half of their sperm has to be heads, 50% has to be tails, same thing down here with the eggs. The probability of getting two heads together, 50% times 50%, gets me 25. All right, same thing with everybody else. What if I want to know the probability of getting a homozygous dominant and getting a homozygous recessive? Well, now I'll add these two together. Okay, and that's the idea of these rules of multiplication and addition. And so we can apply these rules to predict the outcome of multiple characteristics, dihybrid, trihybrid, 4 characteristics, 5 characteristics at a time, without having to draw all of those boxes. So I can do a single monohybrid cross for each trait that I want to know simultaneously, get the probability from that cross for that one trait, and then use the laws of probability to start figuring out, all right, I wanted to really know 3 different characteristics. So if I figure out the probability of one characteristic at a time, and then use the laws of probability, I can figure out what the total probability for my original 3 traits is based on, using each 3 independently. And we'll do some practice with this. But here's an example. Okay, so I'm calculating the chances of a variety of phenotypes using 3 characteristics. And so I can use those single monohybrid crosses, those monohybrid Punnett squares, the little 4s, and consider each probability separately, and then multiply them together to figure out what the actual chance is. So if I have an individual who's like this, and I want to know what the probability is of getting at least 2 recessive traits as a whole, okay, then I can take this opportunity, this option, I get a quarter having 2 recessives, half getting 2 for this, and half of them getting this. So it gives me multiplication of 1/16. It could also look like this, another 1/16, and so on and so forth. Add these all up, and that gives me 6/16 or 3/8 of the possibility that from these particular situations, I can get an organism with at least 2 recessive traits from these 3 different characteristics, and I didn't have to do a giant Punnett square to figure it out.